This morning's class is going to take a little bit of a deviation from what we have been talking about, just so that we can set some context in terms of the fundamentals or the theories that undergird spectroscopy. Now, it is in no way my intention to have a full-out physical chemistry class, but it is appropriate for us to speak to the origins or the theories that undergird spectroscopy in the first place. Going forward, you will find that the various spectroscopic techniques that we encounter will be centered around theories that have been birthed out of quantum mechanics. And so we do need to have somewhat of a conversation regarding the quantum mechanical components that govern the spectroscopy techniques or the spectroscopy mechanisms that we are giving attention to. Just in the way of announcement, one of the things that I need to let you all know is, as we've spent quite a bit of time on IR, and rightfully so, we are actually not going to be giving every single spectroscopic technique listed on the course outline this depth of attention. The reason why we are giving focused attention to IR is because it has significant utility in organic chemistry and in the elucidation of compounds. However, as we go further, and actually between today and tomorrow, we will be wrapping up this portion of the course. So we should have covered everything pertaining to IR by tomorrow. And going forward, you will find that there will be some of the concepts that will be repetitive, but not that many. Our hope is to then apply these take-home messages, if that's the word, towards structural elucidation. So announcement-wise, what you will be getting at the end of this section, which will be tomorrow, is an actual assignment where you'll be allowed to apply the techniques that we've learned and we are learning towards real-life situations or real chemical molecules in terms of context. And then we will also have our discussion with regards to the test, because by the end of tomorrow, we will have covered enough material to allow us to have our first test. Okay, so that's for announcement purposes. The next technique that we will look at after this will be, I'm thinking it's either going to be UV or NMR. I'm not sure yet, but I will definitely keep you guys posted. All right, so today's class is going to be centered around building or filling the gaps with regards to the foundation pertaining to spectroscopic techniques, and more specifically in this case, infrared spectroscopy. And so one of the things that we will do is we will start off discussing some of the assumptions that have been made or that were initially made in classical mechanics, and essentially give some kind of observation or attention, to how those assumptions would have been required or would have been challenged first, and then would have had to have undergone some kind of adjustment to accommodate the actual realities that represent our world. And so that will bring us into a brief discussion pertaining to quantum mechanics and how quantum mechanics provided some kind of respite, if we can say, pertaining to the limitations that were presented in classical mechanics. And of course, it would be remiss of us to have this type of discussion and not touch on the Schrödinger equation, not from the standpoint of derivatizing it or doing the mathematics, but from the standpoint of its application, its utility, and how it has served to be able to provide us with the tools that we are now able to rely on so consistently in our work. All right. So essentially Schrodinger equation and how it has been used to amplify the concept of quantization, as well as selection and selectivity in terms of how energy is accessible in specific ways in systems. All right. So we know about quantization, but Schrodinger's equation now allows us to be able to display that quantization in ways that are unique and specific to every individual system. While we know that no two systems are alike, we do know that they also have similarities with respect to the principles that guide the dynamics of those systems. We will then get into a little bit about wave functions, not much, just probably a cursory mention, and eventually sort of segue into, not segue, but come back to our home base with regards to spectroscopic implications, because literally it is as a result of the quantum theories that undergird classical mechanics that we are now able to make use of these theories and apply them spectroscopically. Okay, so as you can see here, the outline allows us to identify, first of all, that there are some correlations between the quantum numbers that you would have learned about in first year chemistry and they're now, not they're now, but their application or the utility that they're able to find in giving us spectroscopic analysis and spectroscopic tools. So without further ado, we're going to proceed, and essentially our first conversation topic today stems around going back in history around the 1700s, where Isaac Newton was the father, or seen as one of the fathers, of classical physics / mechanics. Now, when you hear the term mechanics, or, well, yeah, mechanics or dynamics, it pretty much is intended to speak about the movement of the components of a system, how those components move, how they actually, what are the implications of their movements, what are the not motivations, but the triggers or the reason for the movement, how that movement is actually taking place, what's the actual reason for it to occur and to stop. And so, of course, you will have had some kind of exposure to Newton's 4 laws that govern motion, that describe motion. And one of them would be, right off the bat, an object that is in motion will stay in motion unless it is stopped, or the converse, which is also true, an object that is at rest will stay at rest unless it is stopped. So essentially, one of the assumptions that Newton made and classical physicists made was that whenever something is coming in contact with any form of energy, or should I say, before I talk about that, one of the things you have to bear in mind, if you haven't already recognized this, is that when something changes its position, it is also changing its energy. And so it is important to note that even if the focus of that observation is on one aspect in terms of the positional change, it's important for you to recognize that at the same time, when the position of any object, large or small, is changing, there is a corresponding energy change that is taking place as well. So in macroscopic systems, as in the world that we see and feel and touch, that is easy to relate to. We've been able to identify forms of energy, kinetic and potential. We know that when something is in motion, it is heavily, the energy component that it is actually interacting with or experiencing the effects of is heavily kinetic. And when the object is at rest, the component of the energy that it is actually experiencing or interacting with is potential. And so we can see then that along with dynamics, that as the dynamics of the object changes, so too will the energy. And so Newton's assumption was that all energy basically is present in a continuum, meaning that it's not discrete, it's just pretty much gradations going from one level, not one level, but from one degree to another, but it's fluid. And essentially the assumption extended to include that the fact that when this continuous form of energy presented itself to matter, the interaction between matter and energy or any form of energy was no different. And so this was actually one of the principles that undergirded what is called the equipartition principle, which means basically that energy is accessible to all matter at all times without interruption and just continuous in its interaction or exposure. Of course, now we know that that's not the case, but that was the underlying assumption that classical physics was based on in that time. The second key assumption is that, or was that, all forms of matter could exist positionally, any and everywhere without restrictions. Now, I'm not saying any and everywhere at the same time. I mean that what I'm saying here is that there was no place that matter could not exist. All right. So there was no concept of an electron, for example, not being able to occupy any part of the atom. The assumption was that the electron could be anywhere in the atom without any restriction. And so as I speak to these things, I'm going to try as much as possible to keep it within the context of our chemistry, of course, helping you to recognize that the assumptions that we would have been, not the assumptions, but the conclusions and the proposals and theorems that you would have been exposed to actually came from somewhere. And the somewhere that it came from would have been based on the classical mechanical theories that pre-existed what we now know today as quantum theory. All right, so without going into the literal details of what the early models of the atom look like, it is important for you to register the fact that the atom, for example, atomic structure has evolved significantly from the days of Dalton to now. And one of the assumptions that Dalton made, for example, was that the atom was a hard sphere that basically was something like a billiard ball, and it was called the billiard ball model. Eventually, we got to the Bohr atom, where he did account for the presence of electrons, but that he identified them as being present in orbits and discrete paths and those types of things. All right, so we're not going to go too far into that. Just know that these two assumptions were the assumptions that actually undergirded where all the descriptions of movement in a dynamic system came from. And so that's where we would have had some challenges, or where challenges would have presented themselves in the early days. So some early experiments were done that showed classical mechanics could not explain everything. And so among these experiments would have been the one that was centered around would have been around the one that was centered around, what am I saying? One of the early experiments would have been centered around the concept known as black body radiation. Now, it was well known by observing the physical world that when an object, a heat object, is observed, obviously a heated object would have a corresponding temperature characteristic that would allow it to be identified as hot. But in addition to that observation or that characteristic, the other observation that was made and is made was that there is a corresponding color that aligns with that temperature of the object. And so the conclusions that were observed across the board were that hot objects glowed red and hotter objects glowed white. And so it's actually something that was noticed across interactions with the environment and the world, so to speak, that there was a consistency in terms of the color that was emitted, the color of radiation that was emitted when the object was a specific temperature. And the hotter the temperature was of the object, the more the color would shift towards the blue end of the visible spectrum. Of course, by then, during that time, it was already known that there was a corresponding relation or correlation between wavelength and energy. And so the observation was being recognized that as objects got hotter, the radiation they emitted would have been of a higher energy and a corresponding color that was associated with that energy. So this would then mean that that correlation existed, and classical physicists sought to actually now explain this correlation. And so the guy who would have taken the lead in that would have been Lord Rayleigh, and he uses the equipartition principle to explain this radiation. And so he's basically observing the results, not the results, he's actually observing what is taking place naturally, and he is seeking to now explain this observation by using classical mechanics and the mathematical equations that were available at the time to explain the dynamics and the behaviors of systems at that time. So his assumptions would have been based on the fact that energy is accessible to all forms of all objects at all temperatures at all times without limitation. And there were some challenges that this assumption would have presented, which would then cause his conclusions to be inconsistent. So essentially, what classical mechanics would have then suggested was that because of the equipartition principle, it didn't matter what type of the radiation was, it would be emitted at all temperatures from every object without a restriction. So in other words, the observation was that hot objects would emit radiation that was red in color, and that as the object became hotter, it would become whiter in color. That was the observation. The explanation, however, did not bear witness to that. Classical mechanics, because of the assumption that energy was available and accessible at all times to all forms of matter, basically would now suggest that, listen, you know what? The energy that's available would not just be dependent on temperature. This energy that would be emitted by an object would be emitted every single moment at every single temperature, irrespective of the conditions. And the implications of that were actually pretty catastrophic. because it was suggesting that if something could access, if an object could access all forms of energy at all times, irrespective of the temperature that it was at, it would mean that all objects would be glowing, first of all. It would mean then that all objects would be emitting all forms of radiation, including the ones you cannot see. So your X-ray radiation, your gamma radiation, your micro radiation, your radio radiation, all forms of radiation would be constantly emitted by the object, because there would have been no restrictions with regards to where and when and what is accessible. That would have been referred to at that time as what is known as an ultraviolet catastrophe, because it is suggesting that even cool objects would be generally emitting visible light and other forms of radiation. Of course, today we know that that's not true. But it was what they had to work with, so that's what they were going with at the time. And so what you have here on this, the right side picture of the screen is an actual depiction of what was taking place. So the blue curve represents the change in what we call energy density or density of states as wavelength occurred, as wavelength changed. And here in purple is what Riley's mathematical explanation would have predicted. And so you're seeing that as the wavelength is getting smaller and smaller and smaller, which we know that wavelength corresponds inversely with energy, as your energy is increasing in terms of, as your radiation is increasing in terms of wavelength, what you are also getting is an increase in energy. Now, his correlation is incorrect, and you're seeing there that there's not a maximum, as is what was being really experienced in terms of physical states. So physically, there would always be a maximum in terms of an upper point where the energy of the molecule, not the molecule, of the object would increase in terms of its energy state. And then as it gets to this particular maximum, it would come back down. His predictions were not along that line. All right, so moving on. We get to the point whereby, of course, prior to this, there was no understanding of quantization. And so equipartition governed all the theories that emerged at the time. But in 1900, Max Planck actually would have been one of the key scientists that now begins to identify the existence of what we now know as the theory or the concept of quantization. And so this begins to become the first time in history when energy is seen differently. It's being seen or recognized, or not recognized, but it's being registered as being something that is not as fluid as it was thought of before. And if it is not as fluid as it was thought of before, that means then that it's how energy would interact with matter would also therefore not be fluid. Okay? And so Max Planck presents to us the concept of quantization instead of equipartition. And he basically is saying that in terms of black body radiation, which that's not the focus of our conversation today, but just because this was the experiment under observation at that time, this is actually the model that birthed the whole concept of quantization, essentially. And so he is basically saying that if the energy that was accessible to the object was limited to discrete values, we know that energy exists continuously, but access to the energy is selective. If we consider the fact that this energy is selectively accessible by the object or to the object, then it means that that would actually be able to explain why it is that only certain objects under certain conditions would glow, and other objects or the same object, when the conditions are changed, they wouldn't glow. In other words, if I were to take, not me, but if someone were to take a rod of iron and have it at room temperature, everyone knows that that piece of metal is not glowing. It's whatever the color it is, silvery hue, reflective in terms of not texture, but let's just say color. And essentially that particular object at room temperature is not glowing. However, once you increase the energy of that object, suddenly the temperature increase, which actually is representative of the energy change of the object, has now along with it a corresponding emission that is associated with the object itself. So as the temperature / energy of the object increased, so too did the emission and the energy of the emission increase. Max Planck would now apply the theory of quantization to actually explain why that was taking place. Not just why, but how, okay? And so the difference between his contribution compared to Rayleigh's contribution was that he assumed that the energy, yes, was continuous, but selectively accessible to the object of matter that was present at that time. And so that then becomes now the emergence of what we now know to be quantization. That begins to explain to us how it is possible for us to see a wave, for example, which is continuous, a continuous entity in a discrete way, and therefore recognize that it has the capacity to be both at the same time. All right, so type a Y in the chat if this so far that we've actually spoken to is clear to you, or if it's making any kind of sense. And if you have questions at this time, I will be happy to answer them as best as I can. All right, great. So I'm assuming then we're all on the same page, and that's a good thing. So moving on, this now, it's interesting because in science, a lot of times we forego the historical transformations that are taking place, and we jump straight into the equations and we go straight into the theories. But it's important for us to take a moment at times to bring context, because context helps to build an appreciation for how theories develop, and not just how they develop, but what type of problems they actually would have brought solutions to. And I think that that helps to strengthen your understanding of concepts as you then become exposed to them in a deeper level. So Planck brings this contribution to classical physics, and begins now to change the community and change the way the community will observe physical systems. And as a result of that, the mathematics is now going to correspond, because as you are aware by now, math, physics, and chemistry tend to work very well together, because the math then helps to bring an actual story to give account for systems that have yet to be encountered by applying variables and making space for variables that have yet to actually be displayed in real life, right? So it's not like I fix the problem when it comes. I will cater for it by actually coming up with a mathematical equation that will make room for things that have yet to even be presented, but that I have an idea may possibly exist. So here it is that Max Planck, let me not be too familiar with him, but Max Planck now provides for us a different mathematical equation that takes into consideration the variation of the energy of the object, and as a result, the corresponding emission that is observed as the energy is varying, okay? As opposed to Rayleigh, who did not take that into consideration. So what that meant is he used a different mathematical equation that therefore did not allow for us to see a corresponding correlation in terms of reproducibility of results. So without going into all the other experiments that would have then presented themselves, there are quite a few. One of the things we can say is we take some of the actual conclusions that were drawn, and those conclusions that were drawn would have shown us that quantization is important in explaining the dynamics of systems. And so this quantization of energy would be what is now responsible for what we are referring to as quantum mechanics. And so out of that comes everything: quantum numbers, quantum theory, quantization of states, position, energy, all of that. But in those early days, it was literally a novel discovery, because at that point in time, the entire community was accustomed to seeing energy, not just seeing energy in a continuous way, but also seeing matter's interaction with energy in a continuous way. Now, as we proceed further, you will see then how this now impacts our experience with regards to spectroscopy and spectroscopic techniques. So in comes Einstein, who basically brings into the community and into the actual science other types of experiments that will now bring this to the fore. And among them would be various types of experiments, including the photoelectric experiment and also emission spectra and so on and so on. We're probably going to touch on it a little bit, but not go into too much depth. But essentially, the take-home point here is for you to see that as a result of that inclusion by Max Planck, which is the theory or the concept of quantization, the assumptions that undergirded classical mechanics will now change. One, though energy exists as a continuum, it will now be seen as being accessible to matter, in a quantized / discrete / select form. Okay, that was a pivotal game changer. The second assumption would actually build on the first, which is that if energy in its interaction with matter only did so in a quantized way, it would then limit the position possibilities of the very matter itself. It would therefore mean that an object would not be able to exist any and everywhere, because wherever it actually is located is dependent on the energy that it is able to access. The two go hand in hand. They're not one and the same, but you cannot have one without the other. You cannot have position without energy, and you cannot have energy without position. And so you know that there are two conservation concepts that you're familiar with. One, matter cannot be created nor destroyed. And two, energy cannot be created nor destroyed. And so in both concepts, there is the undergirding theory or the undergirding principle of conservation. So what you find is there is always going to be, instead of the creation or the destruction of the energy, and likewise, instead of the creation or the destruction of matter, what you have is conservation. And therefore, what we have is changing of forms, transferal, but never destruction or creation per se. And so these assumptions would have emerged as a result of the limitations that were presented by classical mechanics, i.e. through the experiments of Lord Rayleigh and others, and the contributions, therefore, of Planck et al. So essentially, the famous wave-particle duality concept emerges, and from there we are able to recognize that waves are no longer to be seen as singular entities that do not have any other types of properties, but instead, we're now forced to conceptualize waves in a way that would have been unique and different from what they were seen as before. And of course, that has to have been a game changer, because you know, a wave is something that when you see it, it is automatic that you will interpret it in a continuous fashion. To now conceptualize it in terms of discrete units would require a paradigm shift, so to speak. And that's exactly what took place. So what we have is the wave-particle duality, where we are seeing waves as particles. And I apologize for the slide being so compact, but I was trying not to have to put so many I was trying not to make a lot of slides with a lot of things, because I really want to get to the spectroscopic part of things, right? Anyway, so here we have the correlation between energy and position, and here are the, let's say, 5 main players. We have Einstein, we have de Broglie, we have Bohr, we have Newton, of course, and then we have Planck. And these guys, let's say the 4 of them, because Newton came, he predated the Nobel Prize. He came around the 1700s, and the Nobel Prize didn't actually come about until the late 1800s, early 1900s, I think. So all of these guys would have become Nobel Prize winners for the work that they did. But essentially, the point of this slide here is to bring to your attention 3 main concepts. 1, on the left, we have a picture that represents spectroscopic transitions. And these transitions would result from, as you know, bombardment with radiation that then leads to absorption, that then leads to emission or scattering. Okay, so in other words, radiation comes in contact, or matter comes in contact with radiation, and it does so in a quantized fashion. This quantized fashion, where matter is now going to interact with the radiation, has the impact of leading to energy changes in the form of matter. We've discussed this already, so this is not news to us, but it is important for you to understand that the quantization is what makes the quantization is what makes the experience, let's just say experience in inverted commas, unique, or the impact on the form of matter unique. And so we've seen so far that when we take radiation of a specific frequency, i.e. quantized form of energy, and apply it to an object of matter, it has the ability to either rotate, vibrate, or eject, as well as do other things. But we have actually given attention so far to the vibrational impact, that is the outcome of that encounter between matter and radiation. If the radiation that is applied to the matter is not correspondent to the energy gap that exists between the levels necessary to bring about that corresponding change, there will be no effect. And 100% transmission is the result. If, however, the form of radiation matches the energy gap that exists, then the corresponding effect occurs, and we identify that in the ways that we have discussed thus far. So there, ladies and gentlemen, is actually an example of what we have identified as the quote-unquote selection rules, or the selectivity that is displayed by systems. Different types of spectroscopic forms or techniques have different selection rules that govern the quanta of radiation that it will respond to. All right, type a Y in the chat if this is okay, if you're clear on that before I go on. Great. Right, so important experiment, photoelectric effect, basically introduced the concept of wave particle duality. Now, here's the point. I want you all to understand that it is easy for persons to identify the whole idea that, okay, I can look at a person and using the de Broglie equation or the de Broglie relationship, it's easy for us to identify that there is a particulate attribute that corresponds to every wave, and there is a wave-like attribute that corresponds to every particle. But that's because we've been told the story after it was completed. In the time when these concepts were being unearthed, it was actually a significant discovery because, like I said before, paradigm shift required. To think of a wave in the form of a particle was novel. And so the photoelectric effect, actually, the photoelectric experiment is what was responsible for bringing that out, because the photoelectric experiment is what actually allowed scientists to recognize or identify waves in a way that was different from what they're accustomed to seeing. So essentially, the photoelectric experiment allowed persons to recognize that waves have particulate nature or particulate characteristics. And the way in which it did that was actually done through showing the effect of irradiating metal with specific wavelengths of radiation. And so you have a graph here. I'm not sure if it's clear, but we have rubidium, potassium, and sodium that were individually radiated with various frequencies of radiation. And so basically a wavelength sweep was being applied to the metals individually. And it was found that irrespective of the fact that the metals were exposed to this range of frequencies, only specific frequencies led to ejection of the electron from the metal, essentially ionizing it. And so the question, okay, so that was one thing. Surprise, surprise. You irradiate the metal with a range of frequencies, but one or two of the frequencies would actually lead to an ejection / ionization of the metal itself. That was already a big deal. But what was even further a big deal was the fact that in order for this radiation to be able to do this, it literally would have to be seen in a way that was different from how it was seen before. In other words, the radiation would have to be seen as an object that bombarded the actual metal the way physical objects do. And so it would have been seen as if one particle was hitting another particle. And in hitting the other particle, kinetically, there would have been a result that was the outcome of that collision, so to speak. That was phenomenal because no one was seeing waves or radiation in that way before. So, I mean, and understandably so, one would not identify a wave as being an object that could hit something, right? So in this particular case, that was phenomenal because the reality is, one, it was basically as if you can think of the wave as like a marble that was hitting another marble. And yet it's not looking like a marble, it's looking like a wave. This was what the photoelectric effect brought out. It didn't just show that light was quantized in terms of selective packets of radiation. It also showed that light had properties that were similar to matter in the sense of being able to have physical impact. That was a big deal. Of course, one can also say that, all right, it's an object of bombardment. It's behaving that way, but it doesn't have mass. So you cannot measure the mass of light. You cannot measure the weight of it. You cannot take its density in that regard. But one would have to acknowledge that there was a kinetic impact that led to the transference of energy from the radiation itself to the metal itself, leading to a physical outcome in terms of the ejection of the electron, i.e. ionization. All right? So that's a significant experiment that took place there, and so on. Anyway, moving on, de Broglie comes in, and what he does is he confirms that radiation has momentum. Radiation has momentum. Now, this is where your classical physics becomes important, because if you recall from your classical physics exposure, and I'm assuming you had it, you will know that momentum is represented by what equation? I was going to tell you all, but I'm going to let you guys tell me. What equation, what mathematical equation represents momentum? Type it in the chat, let me see. The actual parameter, the variable is P. That's what actually represents momentum. But P is equal to what? Mass times velocity, exactly. So thank you for that, Joanna. So if you have momentum and you're saying that radiation has momentum, it is suggesting that it has mass, which we know it doesn't, but it's certainly behaving as if it does. And so that in and of itself was phenomenal, because now it created the opportunity for radiation to be expressed in a manner that was similar to objects, literal, physical, tangible objects. And later on, we are able to see that the converse was also possible from the matter side onto waves. And so we're not getting into all of that because, like I said, I'm trying to stay on track and get to the spectroscopy part. So we could have that conversation at a different point. Right, so conclusions from these early experiments. One, waves are particles. And the particulate nature of these waves would now afford us the opportunity to have spectroscopic transitions. The spectroscopic transitions are specific they're selective, and they're unique to the radiation that is interacting with the matter itself. Now, of course, unique to the radiation is also suggesting unique to the energy gaps that exist within the object of matter. And that's why in the photoelectric experiment, the form of radiation that ejected the electron from rubidium, the wavelength, or I should say the frequency of radiation that ejected the electron from rubidium is different from the frequency of radiation that ejects it from potassium and sodium and so on. And of course, there's something called a work function, which is unique to the actual metal itself or the element itself. And the reason why it's unique is because that work function is literally the electrostatic charge that exists between the nucleus of that element and the outer electron. And that in and of itself is unique. So this radiation would have to have enough energy to one, bombard the atoms of the metal. Two, it would have to overcome, it would have to be larger than the electrostatic interaction or the force between the nucleus and the electron. And then three, it would have to have enough energy to exceed that interaction or that attraction that exists between the nucleus and the electron. Of course, if you have radiation that actually is just exactly equal to the electrostatic attraction between the nucleus and the external electron, there will be bombardment, there probably will be absorption, but there would be no ejection. And so that's what this picture here is showing us. It's showing you that, first of all, if the photon of energy that is being applied to the metal is less than the work function, which is governed by the nuclear charge, there will be no removal. But if your photon is excessive in that it actually includes the nuclear attraction that exists between the nucleus, the electrostatic attraction that exists between the nucleus and the electron, plus the kinetic energy required to eject the electron, then you will have ejection. If that photon does not pack that exact amount of total energy required, nothing will happen. So in other words, if the photon that is applied to the metal carries more energy than than what is encapsulated in this gap here, there will still not be any removal because it has to be exact, it has to be specific. I might just do a little bit of reading and see if that last statement I made is correct, because I'm thinking that it can be excessive and then the rest be lost in terms of heat. So maybe that may not be entirely true, but at the very least, our photon must include the energy of the work function plus the kinetic energy in order for ionization to occur. All right, so those are some fundamentals that we've looked at, and I am just going to do a quick time check before we continue. I think that pretty much is a good place to pause, and we'll take a quick 5-minute break and we will reconvene. Let's see, it's 24 minutes past the hour. We will reconvene at, let's say it's 10:30 my, that would be 10:30 my time, 12:30 your time. All right, so let's take a pause. All right, so we're back. And essentially the comparison that we can draw, the comparison that we would have actually done between classical and quantum mechanics allows us to be able to draw some conclusions. And there are many conclusions that can be listed, but it's what you have before you here is a select few of them that are significant ones upon which our discussions are birthed or based. So we're saying here that in classical mechanics, one of the main assumptions is that it classifies matter as solely particulate, right? Discrete physical entities that have specific types of parameters that govern them. There are some that you can actually identify right off the bat, visible to the naked eye. Mass has mass, it has density, it has volume. There's a specific boundary and border that governs where the object of matter begins and ends. So if you actually are interacting with any form of matter under classical mechanical assumptions, you would be able to say, or you would be inclined to say, this thing, this particular object has specific borders and boundaries that govern its existence. The second thing is that in terms of assumptions, what that did, or the implications of those assumptions, is that it created limited and anomalous conclusions regarding energy and position. We saw that with the black body radiation experiment. Classical mechanics was not able to explain sufficiently the results that were being visibly displayed by objects of matter on a daily basis. It was able to show correlation correctly for low temperatures. But when the temperatures increased, i.e. when the energy of the objects increased, there was a deviation from what was being observed, and that could not be corrected classically. On the other hand, quantum mechanics classifies particles as more dual in nature, as having a wave-like nature, as well as a particulate nature. And essentially the attributes that show up for the various objects of matter become amplified. So particles would be seen as having wave-like attributes on whatever scale, irrespective of whether it's macro or micro scale. However, when we actually bring things down to an atomic scale, the wave-like attributes of matter become amplified. And this has significant implications for how matter behaves and the dynamics of matter on those scales. Because at that point, this is where energy ceases to appear continuous in its impact on matter. On a macroscopic level, when energy is interacting with matter, it is easy to assume that the interaction is continuous. It is easy to miss, quote unquote, the quantization aspects of energy and its interaction with matter on a macroscopic level. However, on a micro or an atomic level, that is not something that is possible, because the scale does have impact as a result of the fact that there are momentum changes that become more significant when the mass changes. And so that's a whole other conversation when we think about the Heisenberg uncertainty principle, not being able to track the position and the location of an object as its mass becomes smaller because its velocity becomes increased and its wavelength changes and a whole host of other things. Again, we're keeping it as narrow as possible, so we're not getting into all of that. But just know that the main conclusion to be applied here in our context is that on an atomic level, the wave-like attributes of matter become amplified. And as a result of that, that includes then, that then creates other, that has other outcomes. All right, so continuing down the table, we see that in classical mechanics, the electron is identified as a particle, and its path of movement or motion is defined, especially by Bohr, as an orbit. Okay, a specific path, a specific trajectory, and it's in a three-dimensional space, yes, but he would not have, because he would not have seen the electron as a wave, and because he would not have seen its path in a wave-like manner, because he was not identifying it from the standpoint of classical mechanics, the paths were seen as definitive. Now, once it got to the point whereby he had to consider polyelectronic systems, the Bohr atomic model no longer held as true. In the case of quantum mechanics, we are seeing that the electron is described as a wave, and to therefore consider its trajectory, as in to identify its energy and its location positionally, one has to define that movement in terms of wave wave-like characteristics, rather than definitive particulate characteristics. And that has then implications for determining its location and its physical location and its energetic location, so to speak, all right, in terms of what state of energy the electron is in. So that trajectory that the electron is identified as having is recognized and determined to be an orbital as opposed to an orbit. So at this point, it's not as defined, it is not as clear, it is seen as probability paths or probability pathways. And that doesn't make it less reliable than what was predicted by Bohr in his atomic structure. In fact, it gives you more clarity in terms of it being a proper match or more appropriate match to our reality. With, yes, it is true, not as specific detailing as Bohr's orbit would have suggested there is. The third observation or the third takeaway here is that classical mechanics uses Newton's equations and Newton's laws of motion to describe the behaviors of matter in a particulate manner, right? So all of the equations of classical physics, force is equal to mass times acceleration, momentum is equal to P is equal to M times V, acceleration is equal to change in velocity over change in time. All of those are the mathematical equations that would have represented or explained, not explained, but would have actually corresponded to the laws that were outlined in classical mechanics. However, those would have provided limitations in terms of they were actually based on the assumption that matter is particulate, and would have worked and did work for that assumption once that is true. However, once applied to the context of our world, especially like I said, on an atomic level, matter ceases to be dominant in its particulate nature and becomes dominant or amplified in its wave-like nature. Those equations, the concepts remain sound, but the mathematical equations had to be adjusted. And so that now creates a space for the need for Schrodinger's equation, because Schrodinger's equation is heavily based on the fact that matter is wave-like at that scale. And as a consequence of that being the case, the description of the behavior and the dynamics of matter on that scale would have to be, would have to take into account that that wave-like nature. And so the equations then hold true accordingly, based on the same concepts of momentum and movement and force of attraction and so on, but the form of the equation would have to look different. So in other words, a simple example would be Bohr's atom would have described the trajectory of the electron based on an orbit, and the assumption was that the atom was a sphere. So then the circular path that the electron would have been expected to travel would have been pretty much like the circumference of a sphere, right? And then if you were to quantize that, then you would have quantized or integral multiples of that. But the mathematical equation would be that of a sphere. On the other hand, now that we know that our orbitals do not have only spherical, that our orbitals extend beyond the spherical shape in terms of geometry, the equations that describe those trajectories and those movements would have to extend far beyond that. And of course, they take into consideration energy as well. All right, so atomic models, again, like I said, for classical systems, for the classical mechanics, would have only held true for single electron systems, and that's why it's called the Bohr atomic model for hydrogen itself. Once it was applied to helium, there was a breakdown and so on. It still is applicable to single electron systems, but again, the addition of an electron changes the dynamics of the actual structure because it changes the energetics as well. And so what we have is the wave mechanical model supporting single and polyelectron systems. All right, so here are our pictures, and we've come to know these. We know this is the part of the reality that we would have been exposed to initially. In fact, when you're in CXC, this is what you were given. And this was the easiest way to teach students how to account for electrons, right? But the real structure tends to be more along the line of the various shapes that come along with orbitals. And these orbital structures, or these geometric shapes that emerge from the orbitals themselves, come as a result of the Schrodinger equation. So here we need to let you know then that the pathways of electrons have energies associated with them, and they are represented mathematically, and we know them to be called wave functions. Now, these wave functions are associated with quantum numbers. So when you were in first year and you had to learn the various quantum numbers of an electron as well as of a system or an element, it was so that we could get to this point where you can then be able to identify these quantum numbers appropriately in the context of bonding. So of course we have two orbitals represented here. We have a pz and we have a d, x squared, y squared. And you can see that in these orbitals, there are corresponding indicators of where the electron can and cannot be. All right. Now, every element has the same set of orbitals, but not every element has the same set of occupied orbitals. And so that's a part of where now the energy changes begin to show up and the selectivity begins to present itself. Right, so we have our, in this case, what we have here, 1s, 1s, 2s, 3s. Okay, so the places where electrons are not ever going to be found positionally or energetically are referred to as nodes. Now, this is something that wasn't accounted for in classical mechanics. There was no such thing. The only place that the electron was perceived as not being able to exist was in the nucleus. But apart from that, you had electrons existing within the orbit, and the orbit would have had a particular distance from the nucleus for reasons that were, I'm not sure what were the reasons given at that time, but classical mechanics would have actually shown, well, okay, the electron has to stay in circular motion and it doesn't spiral into the nucleus, and that has to do with forces of attraction and centrifugal forces and a whole lot of other things that undergirding that. In any case, you have some nodal planes present within the p orbitals and within the d orbitals, right? And then you also have what we call lobes. But these lobes are actually not even discrete orbits, as you know, they are probability functions. And yet they are a part of the same orbital trajectory that the electron is expected to be able to traverse. All right, now you have two components that make up the wave function of an orbital. You have the radial component and you have the angular component, and that's because orbitals are three-dimensional. And so there has to be a consideration of the distance of the distance of the electron from the nucleus. The nucleus is here at the origin 0, and then the distance is considered the radial distance that the electron is expected to be. So in a 1s orbital, what you have is a distance between, in this particular case, 0 and 5, where r is, where the radius is actually r over a naught. Now, we're not getting into all of this. This is just to give you comparisons between 1s, 2s, and 3s. You're observing here that our radial distance for the 1s is between 0 and 5. And then our radial distance for the 2s begins to sort of go in a similar space, but there are some variances. As you can see, there is a similar radial distance, but then in the case of the 2s, you have movement below the origin, so to speak. Again, we're not here to solve the actual wave functions, so that's not what we're looking at. We're just comparing them. At this point, you have in the 3s, we're getting some kind of presence here as well, around 10. And so as we're going further and further away from the nucleus, we're finding that the probability of the electron existing is actually becoming further and further away, which is actually intuitive. We know this already, but it's good to see it on paper. All right, and the same thing can be said for the 3p, 2p, and the 3d. All right, let's go on here. This is what I want us to look at, the probability functions. So your radial probability functions allow you to be able to see where is the likelihood of the electron existing. So in the case of 1s, 2s, 3s, this should be in the other direction, but it's not. So here in the case of the 1s, the probability of the electron existing between 0 and 5 is high. We know then, therefore, that our 1s orbitals have a shorter radius in terms of density and location of the electron than our 2s. In our 2s orbitals, we have them between 5 and 10, which is pretty much where the dominant positioning is. And you do not necessarily see existence between 0 and this little pump here. The probability exists, but it's not the predominant probability. And then for 3s, here we have more outward from the nucleus. 3p, 2p, 3d. This is not in the order I wanted it, but okay. So looking at 2p, we find the probabilities between 0 and 10 in terms of radius. And then in terms of 3p, it's between more along the line of, let's say, about 7 and 20, right? And so we're seeing that the distance is increasing as the principal quantum number increases. So right here, right off the bat, what you're seeing is there is already inherent selectivity in terms of location. The electron cannot exist any and everywhere. And furthermore, if it's limited in its location, it's therefore limited in its energy. And if it's limited in its energy, what type of radiation is prepared or able to accept to be able to be excited in any way, shape, or form will also be restricted. And that's where our selection rules become important and significant. All right, so we know quantum numbers, N, L, M, L, MS. N, L, and ML represent the trajectory, which is our orbitals, or which represents our orbitals. So you have your principal quantum number, determines the major part of the energy, right? And this increases in terms of integral numbers 1, 2, 3. You have your angular momentum quantum number, which speaks to the direction in terms of the angle. This is Cartesian coordinates now, because remember your orbitals are in three-dimensional space. They're not 2D, they're not flat on a page. They're literally in 3D. And so there's an angle associated with them. And so this basically, again, you know how to derive these, but basically the role of your angular momentum quantum number is to describe the angular dependence of your location, or I should say the dependence of the location on the angle of the actual orbital itself, and how that contributes to the energy of your electron, right? Of course, the energy of your electron is determined by your principal quantum number, and it's also determined by the specific location in terms of angular distance from the nucleus and those things. ML describes the orientation in space of your orbital. So in this particular case, we have the values 0, plus minus 1, plus minus 2, all the way up to L. And essentially the angular momentum is in the Z direction. Now, again, not going into all the details, but to give you a sense that every single quantum number has energy implications. In your first year chemistry class, you would have been introduced to your quantum numbers from the standpoint of the components of the actual atom and the what they meant in terms of designations of orbitals. But it's important for you to now begin to see these numbers, these designations in terms of energetics, because when we're talking about quantization and when we're talking about irradiation, we are actually doing this from the standpoint of we're doing this from the standpoint of what the implications are pertaining to the atom's ability to receive radiation according to the energetics of our quantum numbers. All right. All right. So then finally, so these three, like I said, represent your orbitals, and your MS, or your M subscript S quantum number, represents your electron. It's specific to the electron. So you will remember from Pauli exclusion principle, or the Pauli exclusion principle, it tells us that no two electrons can have the exact same spin. You have your orbitals, S, P, D, F, right? And then within the designation, you have various numbers of them. And so as we have them, you now have to fill your orbitals. And once you fill your orbitals, there's a specific orientation that these orbitals must be filled electronically. That's referred to as the magnetic spin, or the electron spin or magnetic moment. Reason for that is your electrons have electronic charge, but they also have a magnetic component. And the way that your electromagnetic fields interact, they are perpendicular to each other, as we would have seen before. That's what the electromagnetic spectrum shows us. And so consequently, in order for these electrons to be able to coexist in the same space, remember they have the same charge, they would be likely to repel each other. In order for them to exist in the same orbital, they have to be able to do so in a manner that's energetically compatible. And the way for that to occur is by having opposite spins. That's one of the quote unquote compromises for the energetics to be satisfied. All right, so again, here are our functions. So we have angular functions and real wave functions. This is what the Schrodinger equation provides us. And basically this is the Schrodinger equation that has been solved for the hydrogen atom. So you have your wave functions, and these are your, this is the, which one is this? This is the radial component, and this is the angular component, I think. Yeah. So essentially, without going into all, no. Yeah, every wave has a radial component and it has an angular component. And as you know, the Schrodinger equation speaks to the energetics of the molecule, but it can also be expressed in various ways. It can be expressed in terms of time. It can be expressed in terms of location, position, and all different forms of parameters depending on the context that it is being applied. So we're not so much giving attention to what the Schrodinger equation is in the context, but more so to correlate how it has been applied towards giving us what we currently now use all the time. So we take for granted that an s orbital is a spherical shape, a p orbital is seemingly a figure-8 shape, a d orbital is a clover shape, and so on. It's easy to make those assumptions now, but it's important to draw the connection between these pictures and the mathematical equations that actually pre-exist, or that they're conceived out of. All right, enough about that. So essentially, take home here is that it gives us contour diagrams that allow us, that derive or are derived or are derived from wave mathematical or mathematical wave functions. These mathematical wave functions inform us as to where the locations are of the electron, where it can exist and where it cannot exist, where it can exist positionally and where it can exist energetically, and of course, where it cannot exist. All right, and so we know those to be nodes. And so that's why when we look at this orbital here in terms of chlorine, we see a 3s orbital, and we see that the 3s orbital has two nodes. It has one here and it has one here. Then you look at the carbon 2pz orbital. It has one node in terms of a planar node, right? And so you have a lobe here and a lobe here. But the area of electron density, the probability, is more on the inner circle. The 3pz orbital for chlorine looks a little different. titanium 3 plus, dz squared. Oh, this is that, yeah, this is that little ring that tends to be around the plane itself. And so the dz squared orbital tends to look like an amplified p orbital. Then we have, again, so essentially you get the point. These are the contour diagrams that help us to recognize that the nodes exist, and not just that they exist, but where they are located from a different perspective. Also giving us a sense of distance as well, because what you can see here, this is the scale upon which these orbitals are being presented are on an angstrom scale. So that's 1 × 10⁻10 meters. Very small. Oops, sorry about that. So with respect to spectroscopy, I wasn't sure how far I would get today with this, but we're here and we'll see how much more we can do. I don't think we have much time left. We have like 7 minutes, and it's been quite a lot that we've discussed today. So here, essentially, bring this now to where we are. We are beginning a quick conversation about the harmonic oscillator model. And the reason why we're talking about that is because, having now been given some kind of background pertaining to the Schrödinger equation and what it did and what it has done for spectroscopy, we are now able to get a better sense, I'm hoping, pertaining to the effect of quantization. Of course, by now, I'm sure you know. If you knew it before, it has become reinforced further through this discussion that quantization has literally impacted what type of energy is available to the matter that is under excitement, right? And so now to examine the various quanta of energy that becomes available to a form of matter. We basically are just changing sort of the dressing on the outside to afford us different types of impacts. And so when we're looking at infrared spectroscopy, we are looking at excitation, but we're looking at it vibrationally. And so it means then that the radiation, as you are aware, that the molecule is being subject to is of a frequency that's going to cause vibrational excitation. In order for us to examine what that means, we have to look at models that give us information pertaining to that type of excitation. So you already know that we're able to identify the frequencies, and there are frequency patterns. We looked at bending modes, vibrational modes. We are able to calculate the vibrational modes that are accessible to molecules. We've been able to categorize them into groups of linear and nonlinear. And so we have some information, but now we have to tie up those loose ends and basically determine how it is that these vibrational modes have been identified. Not necessarily in terms of nature, but in terms of quantity. Where are the numbers coming from that represent the wagging mode for water, and the scissoring mode, and other vibrational modes that we would have examined already? Where are the numbers coming from for the stretching modes, linear and nonlinear? Non-linear, sorry. Asymmetric and non-symmetric. Asymmetric and symmetric stretching modes. Where are those numbers coming from? In order for us to determine that, we have to again refer to the principles of classical mechanics, which again use macroscopic principles or macroscopic systems to guide us, right? And so the simple harmonic oscillator is the model that's used to reference, it's a model that is referenced to explain what's happening molecularly. So we do know that there are differences when you go from the macroscopic scale to the atomic scale. That's not news to us. But even though there are differences, there are also similarities. And so once we are able to recognize the similarities, we're able to then exploit them to our advantage, right? And make the appropriate adjustments. So here it is that we have diatomic molecules that are referenced to the simple spring coil model. Everybody can recognize and have been, I'm sure, exposed to a spring, a slinky, something that has elasticity of some kind. And what happens is that in the classical mechanical model, we use this concept to communicate the strength of a spring using what we know to be Hooke's law. So classical mechanics applies a correlation between the force of the spring, right, and the force constant. So the strength of the spring really will then, or I should say the size of the force constant will then determine how easy it is to stretch this spring. If the force constant is large, then you will have a tightly coiled spring. If your force constant is small, then you will have a spring that is not as tightly coiled and is easier to stretch. And so that assumption or that model is then extended to molecules. And so the force that is being looked at is the force required to compress or extend the spring. R is the actual length of the spring, right? And RE is the equilibrium length. And we'll talk about what that means when we say equilibrium length shortly. So I said already that strong springs are seen as having large force constants K, and weak springs are seen as having small force constants. In chemical bonds, the spring, quote unquote, is the bond, right? Or the bond is likened to the spring in the model. And in our bonds, they're in constant motion, right? They're always bending, stretching, compressing, they're doing all kinds of things. And so we can't look at our chemical bonds as if they're static, because they're not static, they're constantly moving. And so what tends to happen is we have to look at them in that way, whereby we see their length or the bond length as being an average of the movements that's taking place constantly. So of course you are able to refer to tables that give you bond lengths of various atoms in molecules, and you know that you can get a sense of measurement. But the sense of measurement is not necessarily based on a fixed bond that does not move. It's an average. The general point here, though, if we stay with the assumption that your force constant is correlating to the strength of your bond or the strength of your spring, then essentially what we can then do is apply that to our molecules, and we can see then that molecules such as these diatomic molecules, hydrogen, hydrochloric acid, chlorine, nitrogen, have force constants such as is displayed here. So we have a hydrogen molecule that has a force constant of 509 newtons per meter. Hydrochloric acid, 478 newtons per meter. Chlorine, 320 newtons per meter. And nitrogen, 2241. So look at that. As we're actually going along here, we're seeing that all of these are in the 10 to the second power range. And then when we get to here, we've gone up by an order of magnitude. Of course, the corresponding energy is showing as well. So I'm going to ask you all, this is the last slide for today, but what I'm going to ask you to do is type in the chat, what is responsible for this jump between the top three molecules and the fourth one. What's the reason for this large jump in force constant? Type it in the chat, please. All right, so Surendra, you're saying number of bonds. You want to be more specific? All right, still, I need you to be even more specific than that. Nitrogen has 3, it is true. But it could have had 3 as in ammonia. I mean, we know it doesn't, but what is the unique characteristic about these 3 bonds? That's right. The distinguishing feature between these here and this molecule is that these are all single bonds. H2 is a diatomic molecule with a single bond, HCl, diatomic, single bond, chlorine, single bond, and N2 is a triple bond. And you can see that the corresponding jump in force constant is applicable and therefore force strength. And so that gives you immediately a clue or an indicator as to the energetics, the bond dissociation energy that's present within the bond. Now, we haven't spoken about the IR yet in terms of vibrational frequency, but this is giving us an indicator that we will expect absorptions to show that reflect the bond strength of the actual bonds that are being observed. All right, guys, so I think this is definitely a good place to put a pause. We will pick this up tomorrow. And there's a lot to think about. I will put this stuff on the Moodle page so that you can review it between today and tomorrow. And yeah, that's pretty much what we have for today. I'm going to stop the recording.